because I was mentioning about Kelvin's theorem. Okay. That is, the fluid is initially irrotational. Irrotational means is zero. This is irrotationality condition. Okay. If the fluid is initially irrotational, then it will be irrotational always. So the proof for this is, because this is over a region, that is why you have taken the material derivative or substantial derivative. This is nothing but d over dt of, because circulation is q dot dr. Okay. Now from our momentum equation, we know dq over dt, this is the momentum equation, is minus, because this is nothing but, you know, that delta by delta t of q plus q dot del. Okay, q, right? This is what this is. Now what you do is you take a curl of this, and then because this d by dt and then curl, they are all linear operators, so you can shift them wherever you want, and then you write like this, d by dt of, you take a curl, that is I am taking del cross this, and then take an integral over a area. Okay. That means basically you are calculating the circulation and then n dot dA. And this is again minus, you will have, because dq by dt you are putting del cross. So del cross means that will come here, that same del cross, and integral will be there. So you will have del cross delta p over rho dot nda. Okay, this is a surface. Now you apply Stokes theorem. Okay, because your Stokes theorem says that what, q dot dr is nda. Okay, a surface integral is converted into a line integral. Now this is the surface integral, del cross this, so this will become minus this into del p over rho dot dr. Okay, del p dot dr is nothing but dp, because del p is delta p by delta x I, delta p by delta y j, delta p by delta k z k, and with dot product, that is nothing but dp. Now you know that pressure is only a function of density, therefore this closed integral is 0. Okay, because we said that it is a barotropic fluid if it is a inviscid, and also it's an isentropic flow. Okay, so first we gave that proof, isentropic flow, inviscid, it will give you that pressure is only a function of density. and after that you invoke the Stokes theorem and Kelvin's theorem to show that if my circulation is, if this is 0 initially, it will always be 0, because it will always be 0. If this is initially 0, it will always be 0. Okay. Now, what does it mean? It means is, if my del cross q is 0, this is irrotationality condition. Okay. Then it will remain always. That is the Kelvin's theorem. If this is 0 initially, it will continue to be 0. Now, if you have this condition, curl of a vector is 0 means, then q can be written as a gradient of a potential. Okay. And this potential you call it as the velocity potential. Okay. That's all. Because if this is 0, q will be in this form, because if you substitute it, it will be 0 always, identically 0. Okay. Now, that is how the potential flow has come into picture. So, you said first is inviscid, isentropic, then irrotational. Okay. So, inviscid, isentropic gives you barotropic, that is pressure as a function of only density. Okay, our density is only a function of pressure. Pressure as a function of that relation, P over rho power gamma is a constant. Pressure, density, relationship. Then Kelvin's theorem, that is the Stokes theorem. You define what is circulation, gamma is q dot dr. Then the Stokes theorem comes, because it's the line integral is the area integral. Then you invoke Kelvin's theorem. Once you have proved this much, that my velocity can be written as a gradient of a potential. Okay. That is how the potential flow has come into picture. You call it a potential flow because you can be written as a gradient of potential. Now we will have several derivations. But what is the meaning of del cross q 0? Because you may ask, what is that? Because if you take an aerofoil, I will just briefly, just pictorially give. Because if the flow is coming from, initially flow is static. It starts with a uniform velocity everywhere per feet. Then circulation is 0, because q is same. So you take a closed path. You will take any closed path, your gamma is q dot gamma is 0. But if you have an aerofoil, but please understand this path, if you squeeze it, it comes to a point, it doesn't cross any boundary. And you can take here also it is 0, gamma is 0. Here you take a closed path, here also gamma is 0. But if you take a closed path around this, that means you are crossing the wake. Okay. This is squeezing into a, you have a boundary. Now here you can have gamma not 0, but if you this full, that is the full wake, then what happens is usually when the flow starts, you will have one circulation, or you can say one vortex will shed. This is called a shed vortex. How it is shed, why it is shed, that by experiment you observe. What happens is the flow comes, the stagnation point initially may be on the, because it is at an angle of attack, stagnation point will be here. That means stagnation point is the velocity is 0. The flow will come and then go. Here the flow has to come and then make a turn. Okay. Now making a turn requires enormous force. So this is one of the conditions. Initially when it's set, it tries to go that way. But after that, because you have to have a lot of force, this point, that is due to the viscosity effect. How that is created, that you have to have viscosity. Without viscosity, you cannot create a vortex. Okay. But then slowly this point will move here. That is why the stagnation point, you make it as a trailing edge. But in real flow, it will be something like this. It will go like this. It may extend beyond that. That is because of viscosity and other effects. But here we are neglecting viscosity. When this comes, this is like a flow is going back. When this comes here, that means this vortex, it will shed. And then this point will become the flow. This becomes a stagnation point. And now if you include this, because the circulation initially is 0 everywhere starting, that means if I shed one circulation, I must have an equal opposite circulation to make it 0. That opposite circulation is this. If you take around, that is around the aerofoil, that is like if I have one vortex like this, another vortex must be there, so that the total sum is 0. So this will be around the aerofoil. This is shed. The shed vortex will simply go away, because that is from the speed of flow, it will be taken. But then once it goes far away, the effect of this on the aerofoil is negligible, because this flow, once it is infinity, they will say this goes to very far away. Then the only influence around the aerofoil is this circulation. Okay. We define that circulation as, you must have seen, gamma. Now you say my lift on the aerofoil is rho u gamma. This is what you use. Okay. But only thing is strength of gamma, because you know density, you know velocity. Strength of gamma is dictated by the condition that the trailing edge becomes a stagnation point. This is for subsonic case. Please understand. Supersonic you don't have to. That is what the Kutta condition is. Okay. Kutta condition tells you the trailing edge, you make it as a stagnation point. Then the lift comes out with this. Okay. Now in the case of this is when the aerofoil is steady. That is, it is not moving, nothing. But far field flow is always steady flow. But if it starts moving up and down, the aerofoil is oscillating, then what will happen is you will continue to shed vortices. You will have many. Okay. This is what the trailing vortex. Now you cannot neglect them, because you say there is everything from the trailing edge to infinity. Whatever was shed first, it will be there, and it comes. So it keeps on going. Now the effect of these vortices have to be included if you are doing the unsteady aerodynamic case. Okay. If you neglect that, That is what your quasi-study, quasi-aerodynamic theory, quasi-study aerodynamic theory you can say. Okay, if you neglect that effect directly. So this is where the complexity comes in. What is number one? You don't know the strength and the structure, how it will be. This is where initially for all, later we will develop this theory. The structure we will say that the vortex will always be in a straight line behind the aerofoil up to infinity. And there is no interaction between this and this, because this and this may turn it this way. The structure can change. Okay, that is why those are all complex theories. We will not get into that. We will use that there is no interaction between these vortices. That is like a prescribed wake. This is what is called a prescribed wake. That means the wake structure, I say it will be in a straight line behind the aerofoil. But if it is a free wake, that means I allow the interaction between these. That means they can interact, they can change the orientation shape. Then computationally that becomes more complex. That's why free wake analysis, prescribed wake analysis, all these things are in the potential flow. Okay. Only thing is the strength of the vortex you don't know. That is what you calculate later. Okay. This is what the whole potential theory is about. Okay. You assume a wake structure even in rotor blades. We have something called a vortex theory. And then you use prescribed wake or free wake analysis to get the effect of this. Okay. Now, let us now go back to the formulation. I just want to derive few important things. That is, the key conclusion of all this is velocity is a gradient of a potential. Potential, now I have to develop an equation for the potential, because develop an equation means basically what I will do is we have continuity equation, we have the momentum equation, and of course we got that pressure is a function of density. Okay. But we use these 5 and simply reduce them into one equation. Okay. And that equation will be in terms of V. But in that process you get one more speed of sound comes in. That means you should have another equation for the speed of sound. So we will have 2 variables, 2 equations. That's all. Your full potential flow theory is represented by 2 equations. Whether it is steady, whether it is unsteady, because we are deriving unsteady equation, you will find that these 2 is solved. Okay. Now we will get that equation. So what you do is there are some relationships which we first get. You know that this is your momentum equation. This is delta q over delta t plus q dot del q is minus delta p over rho. If you have a vector identity, this is a vector identity 2 plus 2a del cross A. Okay. Now if A is q, that means del of q dot q. If A is q, you will get del cross q, but del cross q is 0 because it is a irrotational fluid. Therefore, if A is q, if I write this as q dot q, this will become 2 q dot del Why I am writing this is because this term is basically this term. Okay. Now you can replace this, and Q is del phi, automatically del cross Q is 0. So you will get the momentum equation becomes delta Q over delta T plus del of Q square, because Q dot Q is magnitude of Q, that is why Q square plus delta P over rho is 0. Okay. What you will do in this is, you know that Q is del phi. You try to write this expression also as a del of some term. Okay. Then you can take del outside. That means that whatever term inside is constant everywhere, because it is independent of the position. Okay. That is what we will do. Now this particular term, we will write it as delta P. You know that it is P is a function of only density. This is nothing but 1 over rho del P. You can write it as del C rho power gamma, because we said that pressure is some constant rho power gamma. This is the borrowed fluid, and this will become 1 by rho C rho gamma minus 1, you will have into gamma del rho, because I have substituted P in terms of the density. Now this term, if I put it back here, this will become del, sorry, or I will write better, let me, this is delta phi over delta T, because Q is del phi. Then this is Q square over 2. This term I am writing this. So you see rho and rho, is it okay? Delta P by rho, what is it? This will happen what? Till I can write this term as, this is rho gamma minus 2, which I can write it as C gamma rho gamma minus 2 del rho, which is essentially C, I think, gamma over gamma minus 1 del rho power. Okay. Because when I differentiate, that gamma minus 1 will cancel out. Okay. So I am writing it in that fashion, plus C gamma over gamma minus 1 del, I am taking it out, rho power gamma minus 1 0. Okay. See, please note, these are all algebra. Now from now on you will have a lot of algebra only. Now you see, this is the del operator. Del is, it's a I delta by delta x, j delta by delta y, and k delta by delta z, which means this quantity inside can be only a function of time. It cannot be a function of position. So you will write it as delta phi over delta t plus q square over 2 plus c gamma over gamma minus 1 rho power gamma minus 1 equals some function of time. Okay. Now you will also modify this slightly, because you will say, what is the speed of sound? Because I am not deriving it. A square is dp by d rho. Okay. Now P, you substitute this. P is C rho to the power gamma. So you will get actually gamma C rho power. Okay. Now you multiply this by rho and divide by rho. This will become C rho into gamma over, what is that, rho power gamma over rho. Okay. And this quantity is P. So you will get gamma P over rho. Okay. Which is essentially this term. A square is gamma C rho to the power gamma minus 1. Now if you come back here, this is nothing but speed of sound square. So you will have your equation delta phi over delta t plus q square over 2 plus a square gamma minus 1 equals f of t, where a is the speed of sound. Because this part dp by d rho, that is you can prove it. Okay. That is also from momentum theory and basically continuity. Simple. You can show a one dimensional problem. If you write it, you will get the speed of sound is this. Okay. Now we need to, what is this f of t? Because if you say my aerofoil is here, aerofoil or lifting surface, anything, you go to far away, here you write because this is my I and this is my J direction. You can say J, or you can have J there and K here. You can have anything you want. This can be K, this can be J. This is far away and this is minus infinity, because my I always I take it starting from the aerofoil. Okay, so in the far field ahead, the flow is coming steady with the speed u infinity, and you know that phi becomes, because del phi by del x is u, so that is what phi is u infinity x, and the pressure here is P infinity, far field pressure, you may say atmospheric pressure, and the speed of sound A is A infinity. Okay. Now this is at a location far away in the negative infinity. I substitute that condition because phi here is independent of time, because phi is only u infinity x. So this term goes up. Q becomes u infinity u infinity. So my f of t, if I apply this condition at far field, I am going to get over gamma minus 1 is nothing but f of t, which is basically a constant. This is my f of t, but though it is independent of time, that is all. Therefore, my equation becomes, if I sum it up, this one, it will be the condition I get will be basically delta phi over delta t plus q square over 2 plus a square over gamma minus 1 equals okay. So you rearrange this to get a. A is the speed of sound at any point. A square becomes, because gamma minus 1 you multiply everywhere, this will become a infinity square, okay, and then you multiply by gamma minus 1, you will get gamma minus 1 over 2 times u infinity square minus q square, because 2 I have taken out, minus 2 delta phi over delta t. Okay. Now you see I am getting speed of sound, local speed of sound at any point. If I know phi, velocity potential at that point, q is del phi. So speed of sound is given in terms of velocity potential, and this is the far field, this is the speed of sound under standard atmospheric condition A infinity. So this is one of the important relations, okay, please note that. Okay. That is local speed of sound in terms of velocity potential. Now the same equation is used to get the pressure also. That is, what you do is you know that a square is gamma p, pressure over rho. Okay. Now this is gamma p, rho is p over c 1 over gamma, right, because I am replacing density by pressure. Now I will get a square is gamma, this c will go, this is, no, this is what, 1 over, is it correct? Rho is, is it correct? Rho is p by c, p over c power 1 over gamma, that is correct. Okay. Now you can take the c and the p, this will be p, this will be p to the power 1 over gamma, and the c will go to the top, I will have c to the power 1 over gamma. Okay. Now if I take it up, I will get gamma c 1 over gamma p to the power 1 minus gamma, which is gamma minus 1 over gamma. Okay. Which means my a square is pressure gamma minus 1 over gamma. So I can write in terms of a square over a infinity square. This is a constant, they will cancel out, leaving behind p infinity gamma. Okay. Now that is what I am going to write here. You divide by a infinity everywhere. If you divide by a infinity, you are going to get a over a infinity is 1, sorry, equals 1 plus gamma minus 1 over 2, 1 over a infinity square u infinity square minus q square to delta p over delta t. Okay. You just replace this by p over p infinity. Then you will write your relationship. I will write it here itself. Okay. You substitute a over a infinity square in terms of p over p infinity, and then take gamma over gamma minus 1 and multiply by p infinity here. So you will get the pressure becomes p infinity times 1 plus gamma minus 1 over 2 minus q square minus 2 del t okay. This is my full expression. Pressure in terms of, again pressure in terms of potential. Okay. Now this equation can be rewritten in a non-dimensional form as a pressure coefficient, because I will write that expression also, so that we will finish that. Because pressure coefficient, you define Cp as by half rho u infinity square, which you can write it as, because you can say okay half rho, because this is rho infinity, okay, which you can put it as half gamma rho infinity. I am putting gamma p over rho is what? A square. Okay. Or in other words, A infinity square is gamma p infinity over rho infinity. So rho infinity is going to be gamma p infinity by A infinity. I am going to put that, substitute here, gamma p infinity u infinity square over, okay. So this is nothing but Mach number, m infinity square, okay. So this is essentially Cp is p minus p infinity over gamma over 2 m infinity square, even though I use m infinity because the Mach number at far field, not the local Mach number, into p. Okay. Now I can, this quantity you can substitute for p in terms of the entire stuff, okay, and then you will get pressure coefficient, which I am writing it finally as, because p minus p infinity, because I have to subtract one p infinity here. So I will put another p infinity there, minus, then divided by p infinity. That is going to be this quantity minus 1, that is all. And I simply have Cp is, because this is 2 over gamma m infinity square. You open a bracket, open another bracket, 1 plus gamma minus 1 over 2, because this term is gamma minus 1 over 2. If you take the u infinity outside, this is Mach number. So I will have m infinity square, you open another bracket, 1 minus, you combine these two terms, q square plus 2 delta phi over delta t divided by u infinity square. Please understand this, I close now the bracket. This is gamma over gamma minus 1, and then I put another minus 1, and then okay. This is my pressure coefficient, okay, Cp. Why we write all these expressions is because finally we may say these are very small numbers. Q infinity is that the change is very small. Then you can do by binomial expansion and retain only the first term. Okay, instead of taking to the whole power gamma over gamma minus 1. And these are the approximations that are made. Okay. Now you see, we have the pressure expression in terms of potential. That means if I know the potential, I can get the pressure at any point. And if I know the potential, I can get the speed of sound at any point. The next question is, how do I get my equation for phi? Okay. That comes from, we have to again do some jugglery. This is a little bit, because you need to, 1 minute, I will bring it, because this is a combination of your momentum equation as well as your continuity equation, okay, and this is pure algebra. Okay. If you want, I can derive that entire algebra, because this is essentially some substitution back and forth, and at the end you will have one equation for phi. Okay. So now we will just briefly go through that, so that you have an idea of what we have developing. Okay. I erase everything, because we need to have this equation, because we are starting from this equation. Okay. So let me keep, please understand, I leave this also, I erase this also. Okay. I would prefer to have, and I cut it out. Okay. And what you do is, this equation, this is nothing but momentum equation. You can write it in a different form, that is delta t plus q, this we wrote it as del of q square over 2. This term can be written, because that you have to know how to write, because this is again some p reference to p dp by rho. Okay. How this is written, that minus del p over rho, because the minus sign I have brought it here. This particular exercise, this is just some little algebra. Note that I will write this here, and then we can erase it, because you know d over dp of some p reference to any p Okay, this is nothing but 1 over rho, because you are differentiating with respect to the integral. Okay, so you get the same thing. Now, if I write like this, I delta by delta x of integral p reference to p dp by rho. I am writing it as I is the unit vector, delta by delta p. Okay, here of integral p reference to p dp by rho into here because of delta p by delta x. Okay, this is nothing but 1 over rho. Okay, this is 1 over rho delta p by delta x. Okay, that means similarly I j k I can write it. Then that will become I delta p by delta x is what? Del p. Del p by rho is what I have, del p over rho. That is nothing but I del of this integral. I j k if I add, that is nothing but del of this term. That is what I have written here. The gradient of the integral is nothing but this. Okay. Now you again readjust. That readjustment comes because you know that q is del phi. So I can write it as del of delta phi over delta t plus this is q square over 2. You can retain it as q square over 2 plus integral some p reference to p dp over rho is 0, which means this quantity is again independent of the position. That means it can only be a function of time, which you call it another f of t. Then you will say, what is the condition at the far field? Okay, far field p reference to p, that is p reference, this term goes to 0, q becomes u infinity square. So essentially this term, if you apply to the far field, it is u infinity square over 2. So that is your equation. So you will get delta over delta t phi plus q square over 2 plus integral p reference, which is p reference is p infinity, p dp over rho is okay, and this is called the Bernoulli equation. Okay, Bernoulli equation for unsteady aerodynamics. This is what Bernoulli. But even though it is not derived by Bernoulli, okay, this is the Bernoulli's equation. Now, how do we get the final equation? Because this is still used. Please understand, this equation will be used. We will go back and write our continuity equation. The continuity equation is delta rho over delta t plus q dot del rho plus rho. Okay, this is my continuity equation. Here what I will do is I basically go and substitute every term in terms of phi, and that is my final equation. But for that I need to have these things. So you divide by rho. This will have 1 over rho delta rho over delta t plus q dot del rho over rho, because this is del rho, plus del dot q. Okay. Now let us take this term. Okay. What we will do is, I go back here. Let me erase this part. Okay, because it is not necessary now. We need to get, suppose you use this integral delta over delta t of integral p reference to p dp over rho. This you can write it as delta by delta p into delta p by delta t. Then when I do, delta p by delta t will be separate, delta by delta p will be 1 over rho. This will be, actually I can write it as 1 over rho, okay, delta p by delta t. Because I am just changing the, first I differentiate pressure, then pressure, because pressure is, this is only a density, everything is only pressure term dependent. Okay. Now this I will write it as 1 over rho delta rho by delta t. This is dp by d rho is speed of sound. So I will have a square over rho delta rho by delta t. Okay. Now what I will go is, I will go and look at this term. I simply differentiate delta by delta t here. Okay. This is a constant. So from here I will get here, from this equation, if I do delta by delta t, what will I get? This term is going to become, from here I will get delta over delta t of delta phi by delta t plus delta by delta t of, you will have q square over 2 plus, no sorry, I should not put this inside, plus integral p reference p this is delta by delta t u infinity square over 2, this is 0, and this term I can replace a square over rho d rho by dt. Then I will get del square phi over delta t square plus del over del t of q square over 2 is equal to, I am taking this term, that will be minus a square over rho delta rho over delta t. Okay. That means I have an expression for 1 over rho delta rho by delta t as this term. Okay. So I will go and write here. This is nothing but 1 over rho delta rho by delta t. I will write minus what? 1 over a square. Please note that I am getting 1 over a square into del square phi over delta t square plus delta by delta t of q square over 2. This is the first term. Now I will go and replace this term. This is the first term is replaced. Everything has come, rho is changed, phi, q is del phi. So this is also in del phi. Now this term also I will go and change it to phi. And that you do it as, again you go back to, I erase this part because this is now not required. dot del rho over rho. You can write it as q dot delta p into d because p is in terms of rho. Now this is nothing but 1 over a square. This is 1 over a square q dot del p over rho. Okay. Now del p over rho is what? Huh? Delta p over rho. This is from the momentum equation. You will have minus plus q dot, right? So I can directly substitute here q dot del p over rho is this term. So I go and, but of course 1 over a square is there. So I will substitute this term, then this will become minus again. So minus 1 over a square del q over delta t, right? Huh? That is the first term, right? No, I have to get a q dot. There is a, I'll put the q dot, maybe 1 by a square. So I will use a q dot, okay, q dot plus the second this term, q dot of this particular term, right? Because this term is q dot del q. How can you, where is that? That is nothing but del q square, right? This is what? This delta, this we wrote it as q square over 2, okay, this term. So you will have here q dot del q by del t and then del q square over 2 plus 0. Okay. Now what you do is you take this q dot this. Yeah, divergence of rho. No, that is what is replaced here. It is replaced in terms of p. Okay. This p is from momentum equation now. Okay. That's what I am doing. That q dot is always there. I have to put a q. That is why I put a q dot of the remaining term. Okay. Now this entire equation can be written as del q, and this is nothing but q dot, this will go inside. So I will have q dot delta q by delta t, I can have q square. Okay. So I will write it like, and you look at this term. This is 1 over a square del square. This term is remaining as it is. This will be delta by delta t q square over 2. This term is again q square over 2 you will have, because this is q dot delta q by delta t is q square. You can say q dot which is q square. This and this will add, and q square over 2 you will have a q square over 2. Okay. So you will have only q square. Now I can write my full equation like this. Boundary conditions. Okay. I will be able to introduce a little bit today. Now you see, this is all your two equations. All the algebra which we did till now essentially boils down to getting this. Now if you assume my flow is incompressible. That means density is a constant. Then speed of sound is actually infinity. A will go to very high value, this will completely drop out, you will get del square phi is 0. That is why even in low speed, incompressible condition, if you assume, del square phi is 0 for unsteady flow also, but it does not matter. And then you have only phi, anyway A is gone, it is infinity. So your complete unsteady flow equation is governed by del square phi equals 0, that is a Laplace equation. Okay, whether it is steady, unsteady, it does not matter, you have the solution. You have this equation. Only thing is you have to get now the boundary condition. Okay. But if it is a compressible flow, once you go, then you start. That is why transonic. When you go to transonic speed, you cannot assume my Mach number is approaching 1. You cannot make that my speed of sound and the vehicle, they are almost close. I can't make that assumption. Okay. Then basically I have to use the full nonlinear equation. Now what people do is, even in transonic, because this is fully nonlinear, you cannot get a solution. It's not easy, you have to do numerical only. They use a small perturbation analysis. That means my far field, which is u infinity, and my wing and other things, they are all very thin, and because of the nature of the surfaces which we use in the aerospace, we say it is a very thin surface. You make approximation to the boundary conditions. Okay? And then essentially the problem becomes relatively simpler. And that is what is done. Otherwise you have to solve the full equation. Okay? This equation if you solve with the respective boundary conditions. Now we will just describe a little bit about the boundary condition I will introduce, and then what is the nature of boundary condition I will write it. Okay, that equation. Okay. But this is all algebra. Finally, please understand one thing, the algebra is, that is why you get lost in so many differentiation, substitution, back and forth, etc. But that has nothing to do. Finally, you need to get these two equations, that is all. And the whole idea is continuity equation, momentum equation, and we have invoked inviscid, isentropic, irrotational bus. And they brought down to this equation. That's all. And this is valid for any speed, even 0 to Mach 0.3, because so long as you don't have intense heating, isentropic relation is still valid. That's all. Okay. Now let us take the boundary condition. I'll just briefly derive this today. Then we will. Our boundary condition is flow normal to the body should have the same velocity. That is all. In the sense, velocity, please note that velocity normal to the surface of the body. You may call it, if you want to call it, you can say the flow velocity normal to the surface of the body must be equal to the velocity of the body normal to the surface. Okay? Because velocity of the body at a point, you can have components. okay, UVW. But the normal velocity of the body at any point, that is why you have two velocities. One is flow velocity, another one is must be equal to the body velocity. Again normal to the surface. This normal to the surface is, it is there in both places. Okay, body can move like this. Okay, what is the velocity normal to the surface at that time? That is what you have to take at that point. So you have two velocities. One is the flow velocity, another one is body velocity. You basically take the normal velocity at the surface and you say equate. Hey, the flow velocity normal to the surface must be same as the body velocity, which is normal to the surface. That means you have to first define the surface, then you have to find out what is the normal to the surface, and then you take the velocity normal to the surface. Okay, the component of velocity normal to the surface. That is what you will do. Okay. Now the surface of any body is described by, you say f x comma y comma z comma t. At time t, this is the equation of the surface of the body, which can be the wing, anything, because it is a three-dimensional body with respect to some coordinate system. After some time, the body is moving. That means body can deform also. It need not retain its same shape. Please understand. Because what can be a nice circle can become an ellipse. That means your equation is also different. So what you do is, you after some instant you will have another equation. That equation, I am using the same symbol, but my surface now x plus delta x, y plus delta y, comma z plus delta z, comma t plus delta t. Because in a small time increment, I am getting another surface, and this is the, sorry, this delta I should put it, what is that? This delta, I am sorry. Okay. Now this is also 0, because after some time the body surface I am describing by another equation. Now what you do is, in a small change in time, you can expand it like a Taylor series with only first order term. If you expand this as a Taylor series of the first order term, you will get what? F of x comma y comma t plus, you will write delta f by delta x d del x. Okay, plus you will have delta f by del y plus delta f by del z plus delta f by plus higher order terms, and you know that this is 0 and this is also 0. You say this quantity is higher order term, you neglect it, this quantity is 0, and this quantity is nothing but what? Delta f by delta x. This is gradient of f dot delta r plus delta t into delta t. That delta t, you take it, actually what you do is, you retain it as it is equal to 0. This is, you write it like this. Now I will go back here. maybe, okay, I erase this part. Okay. This is my condition. Okay. Now, what is the normal to the surface mathematically? Because what we need is normal to the surface. Normal to the surface is gradient of the function represents normal. Okay. This is the unit normal, therefore I put a magnitude. So gradient of a function is basically the normal, and I divide by that, you get the unit normal. Now what is the velocity of the body? Velocity of the body at any point on the surface, any point on surface, that V is what? Delta R by delta T tending to 0. Okay. That is the velocity of the body. What is the normal velocity of the body? You know the velocity of the body is delta R by delta T. You take dot product of that, you will get V dot N. Please understand, V is velocity of the body. This is delta R over delta T, and the normal is gradient F by mod F. Okay. Now, from that equation, delta R by delta T and you divide by magnitude of delta F, what will you get? You will get here from this equation del F, you divide by magnitude of del F, that by delta T. This is going to be minus F by delta T 1 by magnitude of del F. Okay, that is what is going to be there. So I am going to write this as minus 1 over magnitude of del F delta F by delta T. Okay. Please understand, this is the velocity of the body normal to its surface. That is this term. Velocity of the fluid. Now you go to the fluid velocity. Velocity of the fluid, that is flow velocity. Flow velocity we know, that is Q. Normal to the body means you take the same normal. So you take the dot product, which is so this is flow velocity normal to the body. This is body velocity normal to its surface. These two are equal. Okay, this is okay. Now you cancel out this. You bring both of them one side. Okay. This is the condition. Please understand. The boundary condition is delta F plus this is the So please understand, this is very interesting, and this is nothing but it will look, because del over del t q dot del is nothing but capital D by, you can write it like, okay, it will be like this, substantial derivative. So please understand, there are two velocities. One is the body velocity normal to its surface. Another one is the flow velocity. You have to calculate normal to the surface where you are calculating the body velocity. And this is the equation. Now the whole entire unsteady aerodynamics goes towards, because here it is a Q. Q is nothing but delta. Okay. You need to simply satisfy the boundary condition and your surface. Please understand, the surface is moving. F is moving. Now most of the aerofoil, we will deal with the aerofoil. Aerofoil will take it as a thin plate. And the plate, you can write it by an equation. Because F surface is a straight line. You would normally take it as a plate equation, or if it is a 2D aerofoil, you draw a line. For that line, you can write your equation f of x and how it moves. Then you know the boundary condition, because you know that f how it is moving, and then you write potential, and this should be satisfied. So this equation, now we make approximate. This is where industrial code, what they do is, you in an aerofoil, because our wing is a aerofoil, you have a top surface, you have a bottom surface. That means the two surfaces, you have to satisfy the boundary condition, top and bottom. Suppose if it is a very thin aerofoil, you can project it onto a plate, flat plate. Now, industrial code, most of the potential codes, they don't, even in Boeing, many of the things, all the calculations, they will have treat the wing as a flat plate. Okay. You don't treat them as a three-dimensional body. Because three-dimensional body, then your computation becomes tremendously prohibitive, very expensive. So you treat it like a plate, and then you satisfy the, that is because our wing is not very thick, so you can represent them by a thin plate analysis. Okay, this part we will do the next lecture, because industrial codes, they will try to do, because the potential, of course you can do CFD, you can always say, even Nastran code and many of these codes, they may make their own approximations, okay, in trying to get essentially the pressure on a wing. That is the key. Okay, I think this is enough